Okay. Quick recap. So generative machine learning is about, we have PDFs, different kinds of PDFs, and we have real world signals, which also have their own PDFs. We do not know their analytical expressions, but we know that there are PDFs from where we get the real world samples, for example, images. At the moment I tell you it's a landscape or a scenery or a landscape with hills and flowers, then there is some constraint on the kind of images you can get, right? So we can assume that it's a PDF, like every image, it's a random variable, and the PDF kind of is conditioned on what category it represents. Likewise, you can have text. My text could be conditioned on something, or my text has a distribution. If I show you a sentence and I tell you that this is an English sentence, you know the distribution roughly, right? It won't be, if I tell you a sentence like, I is going, you will understand this is not English or this is not proper English. But I have to say I am going, then it is proper English, right? So even if you represent every word as a random variable, and then this joint distribution has some constraints, and you can define a PDF on what kind of samples you can get, right? Likewise, biomedical signals like EEG signals, ECG signals, etc., etc. So all these signals can be represented by joint PDFs, and you can use PDFs to model them and generative AI to generate samples from them. So many applications, you know the impact of this technology. ChatGPT. How many of you have used ChatGPT? How many of you have not used ChatGPT? You are the only one, sorry. Yeah, you should start using it. No problem, you will make one, don't worry. So ChatGPT is, it models the text as a joint PDF, and then it generates samples from that PDF. And then you have image generation. This is also a model from OpenAI. You give some prompt, like a white Siamese cat or something, and then it will generate an image for you. So generative AI with images is also available. Huh? I don't know. Am I audible? Am I audible? Okay. Audio generation. So you have Alexa, Siri, all of you are familiar with this. They all use generated audio. Means this is not a human being who has recorded that audio. It's all controlled by generative AI. Then okay, this is Amazon Alexa. Then you have physics. In physics, there are very complicated distributions. The analytical expressions are known, but you don't know how to sample them. So generative AI can help you sample those complicated distributions as well. Environmental sciences, you do climate modeling, you do weather monitoring, so many things. They're very complicated distributions. Analytically, they may not be known, but at least you have the data to learn those distributions and sample from them, and then study how will the temperature or how will the climate change after 100 years or something, and so on. There is so many utilities, so much utility. Now, let's talk about sampling methods which are known to us. Okay, we know the goal now. Goal is to generate very complicated real-world signals. Now, what are the tools available to us? Let's start from 12 standard sampling methods. How do you sample a standard PDF? A uniform distribution is a standard PDF. How do you generate a sample from uniform distribution? Uniform distribution between 0 to 1. How do you generate a random sample from there?
Just take some random values from the in that range from the distribution, and then.
How will you take that random value?
Uniformly or the same margin, same difference.
We divide the range by the number of x we need. So we get
No, that is fine. The range is 0 to 1. How do you, if I ask you, give me 100 numbers which follow uniform distribution?
So we can use a random number generator between 0 and 1.
Yes. So we can use a random number generator. So this random number generation is a very big problem. People have already solved it in some way. It's called pseudo-random number generation. And now these tools are available to you in the form of libraries, like NumPy library in Python, or so many libraries are available which will have these functions to generate random numbers from these standard distributions, either uniform or Gaussian, etc. And you can generate samples from there very easily. Just one command, like rand between the range 0 to 1, how many numbers you want. That's it. It will give you the list of an array of all the numbers. Right? So there are available libraries to sample from uniform distribution and standard distributions like normal distribution, etc. But what if PX is not standard? You have real world signals. I want an image of a hill with a river. That's not a standard PDF. How do I generate samples from there? Okay. What can help us? Transformation of random variables. Other things you can remove. Only transformation. Okay. If you don't know Python, just a kind of a short commercial break. If you don't know Python, then you can learn it very easily. There is a short course available which I recorded 3 or 4 years ago. It's available online on YouTube. You can watch it. So you can get familiar with Python in less than an hour. Okay. Now, transformation of random variables. If my Z is a random variable which follows, let's say, uniform distribution, or some other standard distribution, maybe a Gaussian or something, and x is a function of z, and this function could be very non-linear, very complicated function, no problem. And I want to generate samples from pxx. Okay. So I repeat. The question is, I want to generate samples from a very non-standard distribution. If I can represent that new random variable as a function of a known random variable, which means a standard random variable or a random variable which follows standard distribution, if I can do that, listen carefully, if I can represent my x as a function of z, z is a standard uniform or standard normal distribution random variable, then I can generate samples from x. How? First of all, I know pxx. How? By simple transformation of random variables. All of you remember this transformation of random variables? Do you remember from your maybe 11th, 12th standard? So this is the formula that, this formula, do you remember pxx is equal to pzz divided by dx by dz, and on all possible values of z, which map to x, and sum over all of them. And this diagram can help you recall. Let's say this is my z, which follows a known distribution, and I have my x, and this is my f of z. Then wherever, let's say I want to find probability of this particular value of x, then you draw the line and find out all possible z which map to that x. Find their PDFs and then combine them with this formula, and you will get the px. Do you all remember this? Raise your hand if you don't remember this. Don't remember? Oh, really? I thought this is very standard. Okay, so I will begin. Z is a PDF with a known distribution. There will be a Gaussian distribution here. I know how to sample Z, I know the expression for Z. And x is a function of z. Let's say this is my f of z, the function. Like this is my x, this is my z. So I want to find probability of x being equal to this value. What is the probability that x is this value? Right? Okay. What is the probability that z is this value? Simply this. What is the probability that is this value? Means PDF. Now I ask you, what is the probability that x is this value? What is the PDF of x at this value? So the answer is, you find all possible z that map to this x, which means you draw a line at this x and find out the intersection with the curve. All these z map to this x. Right? Now find the PDFs of these z. Right? Take small neighborhoods, and then you find the slope here. So you now p set z divided by the slope, the absolute value of the slope. That is the probability mass contribution from here, plus contribution from here, plus contribution from here. That is total contribution. So this is the formula you can get familiar with. So in other words, if you know z, and if you know a function of z, the function, then I can generate samples for x also. This was about scalars, right? If it is a scalar, then this formula works. But many times we have vectors. Like you saw image, let's say it's 100 cross 100 image, which means there are 10,000 random variables, and you have a joint distribution over them, right? So you can assume that I have a vector of length 10,000 or a matrix of length 100 cross 100 of size 100 cross 100, and then I have a PDF of this vector, right? Which is equivalent to saying I have a joint PDF of 10,000 random variables. Both are equivalent. So, and I will follow this formula. Now instead of taking slope, I will take Jacobian. What is Jacobian? It is element-wise differentiation. The Jacobian of z with respect to x, so where gz is x, and so you take every element of x, differentiate it with respect to every element of z, and that matrix is called the Jacobian matrix. So this is how basically, okay, forget the maths. The idea is that you can know the PDF of x if you know the PDF of z and the transformation. Okay, that was just mathematics. If you didn't understand, no problem. We will, in this hackathon, our purpose is not to become maths experts, but our purpose is to solve the problems. The problem here is you want to generate images, let's say. Let's treat z is a random variable, and it's a known standard distribution. It follows the standard distribution, maybe a Gaussian distribution or a uniform distribution, whatever, and that is my random variable. And I want to transform it into another random variable or random vector x, which is an image of maybe hills or rivers or forests, etc. Right? I repeat, in case you missed it. Z is a random variable which follows standard distribution. I can sample from it very easily. X is a random variable which follows a real-world signal distribution. Right? And now the whole purpose of generative AI is to make this model which can do this transformation. So make this model G generator which can transform this random vector into this random vector. I know the PDF of Z. I have samples of X to train from, and I want to train my G. That's it. So this is a this one approach to solve this problem is called generative adversarial network. This is not the only approach, but this is one approach which we can learn in this tutorial, in this seminar today. This approach was proposed by Goodfellow and team. In the year 2014 it was published. And Goodfellow is, I think, associated with OpenAI now. So what is the task? PXX is the target distribution, and we have samples from PXX. For example, images. I don't know the analytical expression for the PDF, but I have samples. I have images of different hills, different rivers, different forests, etc. But I don't know analytical expression for the PDF of X. So this is the problem. I want to generate more samples. I want to generate more samples of hills, rivers, etc. Solution is choose PC that we sample from, uniform distribution or Gaussian distribution, and then learn transformation G to get X. How do we do it? So we have a generator G. Let's say we use neural networks, convolutional neural networks, etc. to make this generator. It will generate some X in the beginning. It's random. The weights are random. So my input Z will map to some random image, which is certainly not a hill or a river. It's a very random, just pixels thrown here and there. Now I bring in another neural network, which is a classifier. It's called a discriminator. It will tell me whether this X is actually a hill or not. And how does it know? It has some real samples from genuine hills. I have many pictures from hills. It's 10,000 images of different hills. So the discriminator will try to classify whether this X is coming from generator or from the real hills, from the real distribution. That is the task of the discriminator. It's like a policeman sitting there discriminating. Is it a real image or is it a fake image?
But how does he have this data?
So we provide the data. We give the labels.
Okay.
So whenever I am feeding an X from the generator, I will say this is actually a fake image. And the target is known for discriminator. Discriminator learns from it. And whenever this comes, the real image I give, I say this is a real image. So discriminator knows that it's a real image. So it learns from that data. And the goal of generator is to fool the discriminator, which means to generate such nice images that the discriminator is not able to discriminate. Generate such good images of hills that the discriminator cannot tell whether it is coming from here or there. Even if it knows the ground truth, but it will not be able to predict that ground truth. I'm telling you it's a fake image, but the discriminator says, no, I don't think it's a fake image. It basically it's totally fooled. So that is the goal. The generator should be so good that discriminator is not able to distinguish between real and fake. So discriminator basically has a binary output, 0 or 1. It is 0 when it's a fake image, which means the image from the generator, and it's 1 when it's a real image, means image from our real data, images of real hills. And the learning objective. So in machine learning, the philosophy is this. You make a learning objective and then maximize or minimize that objective with respect to the parameters of the model. Like G has some parameters, D has some parameters. If you don't know this terminology, I will explain them in the next section. Don't worry. So this is my objective. I want to maximize minus L or minimize L. So if you don't understand this term, no problem. We will do it later. So now here we play a cat and rat race. So this is the discriminator wants to maximize this objective, which means the discriminator wants to really classify fake and real. But generator wants to fool the discriminator, which means it wants to minimize this objective, right? It wants to generate such nice images that the discriminator is not able to distinguish, right? So they are competing with each other. And mathematically, D is trying to maximize the objective function and G is trying to minimize the objective function. Who will win? G should win. If D wins, then you lose. So D should not win, G should win, and it's your responsibility to make G win. But don't make D so weak that even if G wins, even if it generates very low class images. Right? So D should be sufficiently strong, but not too strong. Right? So that's the stability issue in GAN. You have to make the training very stable. It's an art. Means you have to do some engineering here. Okay, this is the algorithm which we do. For k steps you train D. For one step you train G. And in this way you try to continue this optimization until convergence. Convergence means your G kind of wins clearly and D fails. And then once your model is trained, then just keep sampling. As many hills you want, you can generate from that generator G. right? D can be thrown away. Right? After training, D may not have any utility. G is very useful. Okay, there are some mathematical proofs that does it converge, then the proof is given in the original paper that yes, it converges, but many conditions are there which generally never are satisfied, which means the training is never, very rarely it is perfect to ensure that that convergence happens, but okay, just something. Okay. Now these GANs have some problems. For example, samples may not be precise. There could be unknown biases in the generated values. For example, you trained it to generate different kinds of hills, but it only learned hills with the snow. It never learned hills without the snow because maybe the data was very small or whatever reason. Could be maybe the learning dynamics were such that it could not learn those kind of images. So these are known problems in generative models. Technically, they are called mode collapse, which means they are learning some of the modes, but some modes they are not learning. Right? And another problem is, can we control what we want to generate? I don't just want to generate a random hill. I want a hill which has got deciduous trees on it. Or I want a hill with no trees, only snow. Or I want a hill which is made up of desert or sand. So like that, can we control what I want to generate? So this is the topic of our next talk. We'll do it next time, not today. Controlled generation. Okay, now this was generative AI. Now I want to dwell into some of the basics. What are neural networks? What are convolutional neural networks, etc. So let's see first what are neural networks. Now this is very basic. Those of you who know machine learning, you will just refresh yourself or revise those concepts. But those who don't know, they need to pay attention. What is machine learning? You have some input, some output, and there is a model which you want to train so that the output is the desired one. For example, if you want to generate images of hill, then y should represent images of hill. The goal is to train this model properly. Let's take a simple example of classification. I have three kinds of flowers, rose, lotus, and jasmine, and I want to distinguish between them. Let's say this is the height and diameter of a flower. If I just tell you the height is this much and diameter is this much, can you tell me which flower it is? You have some labeled data available for training, which means if height is this, diameter is this, it's a lotus. If height is this, diameter is this, it's a blue lotus. But if height is this, diameter is this, then it's a red rose. Right? Now I give you an unknown point maybe here. Tell me if my point lies there, is it a rose or lotus? How do you know that? The data, how does data say? Yeah, it will ask the nearest neighbors. Or make a boundary here and say whatever lies to this side of the boundary, that is a rose. Whatever lies to this side of the boundary, that's a lotus, blue lotus. Alright? That's what we do. We create a line and then we ask the line, am I lying this side or that side? And the line will tell you, oh, you are on this side, so you must be a rose. Right? This is the basic building block of a neural network. A neural network consists of multiple such lines which divide your whole space into multiple regions, and each region represents one of the classes for classification problem. Line, what is line? Equation of a line, y equal to mx, y equal to mx plus c, or x2 minus mx1 minus c is equal to 0. And if this quantity, let's call this as f of x. F of x is x2 minus mx1 minus c. If this is greater than 0, it is here. If it is less than 0, it is here. Okay. Sometimes you may be interested in soft classification, which means if my point is far deep inside this region, then I am more sure. But if it is very close to boundary, then I am less confident, less sure. So I may need some kind of soft values. So I can create a function such that if the point is far from this boundary on this side, the value will be close to 1. If it is close to the boundary, value will be close to 0.5. Value is low down here, the value will be almost 0. Almost 0. So such a function is called a sigmoid function, which does that. The sigmoid function is simply this function. It's a differentiable function. It's continuous, differentiable, all those good qualities of function when we give function. And then why do we use it? Because it will give you if the point is deep down in this class, then it is 1. If it is very low, then it is close to 0.
Sir, can you teach the machine only on 2 parameters, just like in last example we teach the machine on diameter and height. So can we have multiple parameters, just like diameter, height, color, diameter, height, and x-ray?
Yes. So okay, good question. Very good question. So this is a function of x1 and x2. If I have n number of input parameters, I won't call them parameters. I will call them, let's say, input features. Parameters are these unknown quantities, m and c. M and c are called as technical, or conventionally they are called as the parameters of the model, and x1, x2 are called the input features. Just some terminology. Okay. So if I have multiple input features, let's say x1, x2, x3, x4, so on up to x10, can you use such a model?
No. Depends. You can increase the dimension or cut it.
Yes. So what you do is you increase the number of parameters. You will make a model f of x or f of that vector x is equal to m1x1 plus m2x2 plus m3x3 plus m4x4, so on and so forth, plus a constant c, means a bias c. So it's a linear equation, but it's okay. It's not linear in technical sense. It's called an affine transformation. Affine means you have a linear plus some bias. It becomes affine. And
Using the input parameter increase the accuracy of the model.
increasing the
Input parameters will increase the accuracy of the
input features or model parameters.
features. Just
Input
like
features.
diameter, height, and color. We
Yes.
add the one more parameter, so
Yes.
it increase the accuracy.
So you are adding more information, so it should increase the accuracy.
Increasing the number of input features also to somewhat imply that number of parameters of the model have increased.
You have to increase them manually. You have to increase them. Okay. So basically, this is a two-dimensional space. So your separator is a line. If you have 3D space, your separator will be a plane. If you have 4D space, it will be a hyperplane. And like that, when you keep going up and up in the number of dimensions, here it will be a higher dimension hyperplane. Like that. Okay, finally we get y is equal to some fx, where fx is sigmoid of x2 minus mx1 minus c. Like that is a simple building block of a neural network. How do we classify this kind of data? I cannot fit a single line into this. What will I do? Take a nonlinear separator. You need a nonlinear separator. And this is what neural network does. So neural network is a kind of nonlinear separator. Let's start from here. Earlier we saw y is sigmoid of wx. W is a vector like all that m1, m2, m3, m4, and c. It weights and biases. So m's are called the weights and c is the bias. Right? Times x, sigmoid of that. Now we can treat this as another kind of feature in it. And then you apply again w2 times this feature vector, then again I apply a sigmoid. So you got two layers of kind of operations. Both these operations are very well known to you. Simply matrix multiplication and a nonlinearity. Could be a sigmoid function, could be any other nonlinearity, but some conditions are okay. It should be monotonous, monotonic, and should be differentiable. If all those conditions are satisfied, then you can use this. So this is a nonlinear transformation. All of you agree with this? Which means it's powerful. And it is differentiable. It is differentiable with respect to x and w, so the parameters of the model. Right? All of you agree with this? That's it. This is neural network. So you can now have different kinds of matrix multiplications. And you can, instead of multiplying the whole thing, you can multiply only 3, 3, 3 like that. Different kinds of matrix multiplication and different kinds of nonlinearity. They will give rise to different kinds of neural networks. That's it. The question is, how do we train our neural networks? So we define a loss function which we minimize. Let's say my loss function could be simply square of y minus y hat whole square. Right? Simply the Euclidean distance between the two. And we have defined a loss function. It is differentiable. Right? And how do we train it? We train it with the help of this kind of gradient descent algorithm. So what this algorithm does is, it says take the value of w, then subtract eta times the slope there. And if you keep doing it repeatedly, you will reach the minimum. Here is a pictorial representation. Let's say I have a w, a scalar variable, scalar parameter w, error function, some kind of curve on w. Randomly start with some w, this one. Right? Measure the slope there. Slope is negative. Slope is positive there. So, which means my minimum should be somewhere in the back side. So I subtract this slope from this w. So w0 is this. I say w0 minus the slope. Let's say slope is 1. So I will subtract 1 from this. I will reach there. Right? Again check the slope. Slope is almost 1 only again. Again subtract it until you reach a point where slope is almost 0. This is the minimum. Right? So this is an algorithm to minimize a function with respect to a parameter. Right? That's what we do in the neural networks. We define a loss function with a differentiable curve, and we minimize it with respect to the parameters of the network. That's it. If you want to read further about this, then there is a nice book, PRML, by Christopher Bishop. It's available online, free of cost. You can read it from there. I think there is a copy in the library also. You can get it from there. Or I have my lectures on machine learning for signal processing course, which you can watch. They're also on YouTube. Okay, this was neural networks. Any questions? Any questions? No? Yes.
The graph that you showed for convergence, it was like this, but suppose it went underneath the axis, somewhat like this, then there's a possibility that you draw a tangent from here, it will intersect here, it will, it will oscillate. That is also possible.
Okay, you're saying that you are sitting here and then you reach here, and then you again reach there, and you keep oscillating. Right? Okay, good point. So basically, we don't subtract the slope directly. We multiply this whole term with some eta, some learning rate. So that even if the slope is large, let's say my eta is 0.1, I only move little bit distance. Or even if my slope is 1, I don't move 1, I will move only 0.1. Right? So in this way I can control how fast or how slow I want to move. And when I am reaching almost close to this point, then I will reduce my eta so much that it does not oscillate, rather it settles down. And so by controlling that eta, it's called learning rate. By controlling that hyperparameter, why it is called hyperparameter? Because I'm not training it. I'm not training eta in this algorithm. Eta is fixed. Or eta is kind of controlled separately, not via this algorithm.
Suppose there was another maxima over that, at that red one, then if you are drawing a line, then it will hit somewhere. So
If you have a maximum, means if you have two minima.
yeah, something like that. And suppose there is not a curve over here, then when we are making a tangent, then it's not intersecting the curve.
Tangent need not intersect the curve.
Well, how exactly have you find
W1. So it is simply W0 minus the slope. Slope is let's say plus 1. So you multiply with eta 0.1. So W1 is simply W0 minus 0.1. So I don't have to find the intersection of the tangent with the curve anywhere. Simply know the value of slope, just subtract it. That's it. Okay. Now we move to the next topic, which is called convolutional neural networks. It's a special kind of neural network. Again, let's say you want to identify this category, the personality. You want to identify this personality in any image. So one method is you train a neural network. That is very inefficient. The other method is, I know there are small components. I can recognize them. Right? I can recognize the moustache, I can recognize the turban, I can recognize the stick in the hand. These are some common features in that image, or in the subset of that image, which can help me recognize this category. So what I will do is, I will define a filter. Like this is a filter. This filter will scan the whole image, and wherever it finds the match, it will give a high value. Right? Before I discuss this, why am I doing it? I am doing it because neural networks are computationally very expensive. Right? Computationally, they are very expensive. Now imagine it's a 512 cross 512 image. What is the input size? 512 into 512. How much is that? 2 to the power 9 is that, correct? 2 to the power 18. It's a large value. So let's say 512 is about 500, so it's 25,000. No, 2,50,000. 2,50,000 input parameters. How many parameters will be there in my network? Much more. It's nonlinear, right? So it's millions of parameters. So it's very computationally very expensive. Neural networks are very expensive. And any help to reduce the dimensionality, to reduce the number of computations, that's very much welcome. So what we do is, to reduce the dimensionality, I don't feed the entire image into one neural network. What I do is, I make a neural network which kind of scans the image, detects the useful features, and then processes those features further. And that is called a convolutional neural network, right? I repeat the important point. I don't feed the entire image into the network all at once. Rather, I scan the image with a kind of kernel, I call it kernel, or we call it small network, which scans the whole image. And then those that scanned output is further processed. That helps us to keep the number of parameters low. And how do we scan? Let's say it's simply a dot product. This is a vector, and take this 3 cross 3 matrix, convert it into a vector, take a dot product between them. So let's take the first one, 101, 010, 201, multiply it with this kernel. What is the output? So 1 multiplies with 1, this is 1. 0 into 0 is 0, 0 into 1 is 0, this is 0 into 0 is 0, 1 into 1 is 1, so it becomes 2, 0 into 0 is 0, 1 into 1 is 1, and both are 0. Oh, sorry, 0 and 2. So total is 3, right? So I put 3 here. Now you move your kernel to the next, jump by 1. This orange circle. Again multiply 1, 1 on the diagonal. 1, 1, 1, 0. That's all are 0 there. So 0. The dot product is 0. Again move your kernel this red circle, this red region. Then again 1, 1, 1. Here also we have 1, 1, 1. So it's 3. Then scan the next row. This one. This blue dotted block. The answer is 1, the diagonal is only 1. Then again move it and you get 2. In this way you scan the whole image. So what are the two parameters or two parameters there. One is the size of the kernel, the other is your stride or your jump. How big is your jump? Are you jumping after every column, every row, or are you jumping every 2 columns, 2 rows, or 3 columns, 3 rows, etc. So stride is important. If you use a stride of 2, then you get this output.
So how is that matrix X related to the previous image that
Previous image. This image.
yeah, how is that matrix X related to
Okay, this X is my original image, the original big image, right? Sarah Chaudhary standing with a mustache and turban and everything, the whole image. And this is a small kernel. Maybe it is just the turban portion, right? And it will scan the whole image. Somewhere it will hit the right turban and it will give a very large value in the output. Or maybe it is not turban output, it's just an edge, a vertical edge, let's say. A vertical edge. And then wherever it hits the vertical edge, it gives a large value. It could be anything. And in neural networks, what is learnable? This kernel is learnable. Right? This is the unknown parameter or the trainable parameter. And you will train it in such a way that it detects the image, detects the person. Now, nobody asks you to use only a single kernel. You can use multiple kernels. Let's say this is my input image, this is my kernel. I can use multiple kernels. This kernel gives an orange output, add another kernel, it gives a blue output, another kernel gives a red output, another kernel, keep going, it will give you multiple outputs. Then you can further do kernel action on them, which is another convolution layer, or you can simply flatten them up, which means this block can be made into a vector, a linear vector, and then apply a tensor layer on that vector to classify whether it's Sarah Chaudhary or not. Right? So this is a convolutional network, this part, the scanning part. You can apply nonlinearity also there, like sigmoid or whatever. And then this is the dense part, the ordinary neural network, the dense neural network, fully connected neural network. Okay, sometimes you have colored images, or most of the times you have colored images. So the size of the image is I cross j cross 3. These are the 3 channels which you have. So which means your image looks like a block. It's not a 2D matrix, but rather it's a 3-dimensional block. So what you do here is you have a block, then the kernel also has a block. And its dimension will be, let's say, f cross f dash, let's say 3 cross 3. And the depth here should be same as the depth here. We are only convolving about this w and h. We don't convolve across the depth. Right? So the depth of the kernel is same as the depth of the input in 2D convolution. So which means for images always. Okay, a very quick quiz. If this is my input image, I have used 5 kernels of shape 3 cross 3. Let's say the dimension here is 10 cross 10. What is the size of the output here? Huh? This is 10 cross 10 image. I have used 5 kernels of shape 3 cross 3. What is the size of the output? Huh? 7 by 7. 8 by 8. 8 by 8 by 5. Yes. So it is by 8 because it will be 10 minus 3 plus 5. 10 minus 3 plus 5. So 8 by 8 cross the number of kernels. So 5 kernels are there. So this is 8 by 8 cross 5. Now this kernel is also 3 cross 3. The depth of the kernel has to be 5 because the input is has depth 5. So 3 cross 3 cross 5. And what is the output size here? I have used 4 kernels. 6 cross 6 cross 4. 4 kernels. 6x6x4. Okay, if you understand this, then you are done. That's it. This is neural network, convolutional neural network. Now, if you want to read more about CNNs, then these are some lectures which you can watch. There are tons of blogs and videos online also which you can watch. No problem. Okay. Now we are done with the theory part. Now Pratikya will come and will show you some demo of how you can make a real generative model in TensorFlow. Before she starts, you can just wait 2 minutes. I will just now summarize everything. So we discussed introduction to generative AI. We saw transformation of random variables in vectors. We saw GANs for sampling, GANs for generative AI. We saw neural networks. We saw convolutional neural networks. Now let me announce the hackathon, which we're going to have. So in this hackathon, we will share some data with you. This data will be alphabets of English language. And you have to make a model which can generate images of these alphabets in different fonts. It is not controlled, which means you can generate anything, whatever you like, which means it should be English alphabet. You train it with that data. The deadline for submission will be Monday, which means day after tomorrow, 10 p.m. Right? So you have 2 days to learn Python, you have to learn TensorFlow, to learn CNNs, to learn GANs, and then to work on this problem. Yeah, and to help you, we have demo. You don't have to build everything from scratch, right? You are learning things which are already existing. You're not building everything from scratch. So these are the tools are there, just read through them, understand them, and you are done. This is the preparation. Then we have the final challenge. It's hackathon number 2, which will be on next weekend. This will be controllable generative AI, a kind of real problem. Not a toy problem, a real problem. And those who complete hackathon 1 will receive certificates. They will receive enrollment for hackathon 2. Others will not be allowed. If you don't submit hackathon 1, then you're not allowed for hackathon number 2. And those who do well in hackathon 2, they will get certificates and awards. And then the next seminar will be next week on Wednesday evening. So on Wednesday evening, we'll meet again, and I will be discussing controllable generative AI. Like some.
Just add that hackathon 1 will be only for completing, like it's not evaluated.
Yeah. Hackathon 1 is just for completing the challenge. Even if your outputs are blurry, noisy, whatever, doesn't matter. Just complete it so that you learn the whole thing. And hackathon 2 will focus on results also. Right? Hackathon 1 is just a learning experience for you. Okay, what are the next steps for you? So join this MS Teams. How many of you are there on IITK Office 365? Raise your hands. Okay, how many of you are not there? Not many. But if you are not there, then go to this link, IITK Computer Center link, and enroll yourself on Office 365. And then you can join our team. We have made a team on Office 365 or MS Teams. Join this team, and we'll communicate over this team. Then start learning and building. Any questions you have, shoot on the MS Teams. And if you know the answer, if some of you know the answer, reply to that. And you will see how well you are participating there. Which means those who give good replies, they get kind of good, what do you say? We recognize them. We recognize that these people are also helping others to grow. That's it. Now we will come to the demo part. Oh, how do I do it?
You can click on the link.
Hyperlink, open up.
So this will also come in the recording, or is it?
I think so. I think it will also come. Okay, so this is Pratikya. She is a BTech MTech dual degree student here, and she has been working on generative AI for several months now, and she's an expert.
Am I audible? Okay. So this is like a short demo, like it is based on one kind of a GAN implementation, which is called DC GAN. So it is its full form is Deep Convolutional Generative Adversarial Networks. So this is like a standard. It was also like published few years back, and this has like performed well in various kinds of generative machine learning problems. So that's why like it's already available on TensorFlow tutorials. You can go through it there also. So this is just like we'll go through it so that you guys are familiar with the TensorFlow framework and can start building from here for the first hackathon. So like as sir has already described, so this is basically the GAN model. GAN model consists of a generator and a discriminator. So in the case of DC GAN, both the generator and discriminator will be deep convolutional networks. As the framework has already been described, we will just see how the code looks for that. So like you can go through it. The problem which we are solving in this tutorial is generating MNIST dataset. Like MNIST dataset, if you are familiar, it's like handwritten digits. So 0 to 9, these digits are there and they are in handwritten format. So MNIST dataset consists of all these kinds of digits, and the goal of the generative model here is to generate these kind of handwritten digits on its own. So like the code is in TensorFlow. If you guys are not familiar with it, then over these 2 days you can just go through it. It's not very difficult, and several tutorials are also available, and you can also post questions on your doubts if you are facing in the MS Teams. So we'll be able to answer there also. So these are some libraries which you can install, and these will be helpful for visualizing and also for running the codes. Now here, this particular line, here basically the TensorFlow library is already providing the MNIST dataset which we'll be using. So with this kind of a function, you can load the dataset. So we are only training these images and seeing. That's why like the train images and training labels. The train images will consist of the images of the handwritten digits, and labels will be, let's say, 0 to 9. So these will be used for the dataset preparation and training. So here in this line, we are like reshaping the images to our required format. Let's say every model will take a standard format of the input. So we are creating that kind of standard image. So let's say this is a pre-processing step, which every okay. Is it okay now? Like everyone can see, right? The last benches, they can see the codes, right? Yeah. So basically this part is this cell over here. It's doing the pre-processing. We are like converting all the images in the data set to the standard 28 cross 28 size, so that we can pass it to the model for the processing. Now these are some standard things, you can go through them. TensorFlow dataset will be provided, like the trained dataset that is written over here, that will be used for iteratively going through the dataset while we train the model. These are the dataset preparation parts. Now we come to the main part, which is the generator. The generator here is based on DC GAN model, as I talked about initially. So these are some of the layers of the model. So if you remember the layers that sir was talking about, we have various kernels, and we have like one layer after the other, and the activation functions. Activation means, let's say, the sigmoid, or we have other kind of activations also. Here it's leaky ReLU. So like a brief run through of the code will be like, first of all, we pass the model one input of a 28 cross 28 images, like the handwritten digit. And in the first layer, what happens is that the image is flattened into, let's say, some kind of like it's flattened, the 28 cross 28 image is flattened, and then it is passed through, like after some changes to the input, it is passed through the first layer, which is the dense layer. Dense layer is basically the fully the layer that I think you remember from the lecture. It is like a fully connected layer, and these are the number of neurons which will be inside it, 7 cross 7 cross 256. Then we pass it through something called batch normalization. Batch normalization, basically, if you have a batch size of more than 1, then it normalizes the entire batch, and then that is passed through the further layers. Now the paper, if you want, you can go through DC-GAN paper. These are some some kind of tweakings that the model that is done to the model. Batch normalization is added so that the training is more stable for GAN, because GAN training is highly unstable in general. So these are some of the experiments that people have already done in their research work and have found out that using batch normalization actually stabilizes the training and so on. So that's why they have put it over here. And then leaky ReLU is kind of the activation function or the non-linearity introduced over here. Now these are passed through several other layers. Now one new kind of layer is the conv 2D transpose. Now in our case, we want to produce a 28 cross 28 image using the model. So the conv 2D transpose is actually upsampling this image by, let's say, if the stride is equal to 1, then it's not, but if the stride is equal to 2, it will upsample the image size. Now in this assert layer, you can see what the output of the model should be during that time. Assert is only used to, let's say, verify the whether the model is actually producing that output or not, and let's say if it doesn't, then it will throw out an error so that it's easier for debugging and everything. So the output of this layer after the conv 2D transpose is 7 cross 7 cross 128, and then after another conv 2D transpose, it is upsampling it by, let's say, 2. So by upsampling, I mean the size is increasing from 7 cross 7 to 14 cross 14. And after another upsampling which is run here, the size is increasing by 2 again. So it is becoming finally 28 cross 28. And the last, this first one, let's say here we have 64, here we have 1. So this represents the number of kernels. So in the lecture, sir was referring to 5 kernels, 4 kernels. So the first one here is the number of kernels that we are providing. So based on that, the output size is also changing if we can follow. Like here the 128 kernels were used, so this output shape has 128 at the end. Here 64 kernels were used, so 64 is coming out at the end. And the 5 cross 5 that we are seeing over here, that is the kernel size. So we are using a 5 cross 5 kernel here. And the stride is 1 cross 1 comma 1. That means for the rows we are going by 1 stride, and for the columns also we are going by 1 stride. So this is the generator part. So what exactly it is doing is basically it is taking one noise vector and it is converting that into the MNIST image. So first the model is untrained, so it is not able to produce any good output. Here you can see it is taking some random noise vector and it is producing this noisy output. So this is not resembling the MNIST data set in any way.
So one question.
Yeah.
So all these choices 7, 7 and
Yeah.
other numbers, actually those they have come up with.
This is based on completely based on the research that they have done. They have found out that these kind of hyperparameters, they are giving better results than anything else. So this is a standard DC GAN implementation. In the paper itself, you can find these hyperparameter numbers. They have already given the details. So these are kind of parts of the experiment. You can change these values and see what kind of inputs you are getting. So here you can see initially with the untrained generator, the output is very noisy. Now we are going to define the discriminator. Discriminator is the role of the discriminator is to classify whether the image generated by the generator is real or fake. So this is also based on the paper, and it contains convolutional layers, which you can see the conv 2D part described here. These are convolutional layers. It contains 64 kernels and 5 cross 5 size kernels. Stride is 2. So this padding part is basically representing that in case you want to keep the image size to be 28 cross 28 after applying this layer, then you can add something like padding is equal to same. So you can manually also do padding using other kernel like other functions available in TensorFlow, but this is just one easier way to like keep the size same if you want. If you put padding is equal to same, then the output of this layer will also be the same as the input size, which is 28 cross 28. And then you apply these activations, and now comes dropout. Dropout is another kind of a regularization function, which I think sir did not mention, but it's like something that you want the model to be well generalized. You don't want the model to like learn very fixed kind of patterns. You want to generalize more, so you can add these kind of layers. So the dropout layer basically, if you have a bunch of neurons in one layer, then the dropout layer will remove some of the neurons, or let's say put its value as 0. So in this way, like it does it randomly, so the model is not learning anything fixed. Like the model is not biased to pick up any one neuron to produce its output. So these are some kind of ways that the model can be made to generalize on what kind of output we want to generate. Now these are the few layers, and finally it is flattened. By flattening, like you are converting one, let's say 2D image into one vector. After that you are passing it to a dense layer which has only one output. Now why one output? Because we only want to produce, let's say 0 or 1. Because 0, if it is 0, then that means the discriminator is saying that whatever input was provided, that is fake. If it is 1, then the discriminator is saying that it is real. So this is the discriminator network, and now you can see that if it is an untrained model, like untrained discriminator, then it is giving some kind of random output. This is not representing any whatever we want. We want it to be 0 for generated image, and wanted to be 1 for the the real image. So this is kind of an untrained image. The decision does not make any sense over here, but after training, the model will learn which one is real and which one is fake. Now for training any model, we need to define a loss function. So because we want to train them using, let's say we are classifying between 0 and 1, we are classifying the images to 0 and 1, so we define something called a binary cross entropy loss function. You can go through it later while you are implementing things. So this is basically binary cross entropy means we are saying that the model will have around only 2 kinds of outputs, let's say 0 or 1 categories of the outputs. So this kind of a loss function will be able to inform the model that whether it is predicting that kind of output or not. From logits is equal to true will actually say that like if you are applying here, if you remember, we are passing this kind of a output. We are the discriminator is producing the output from a dense layer. We have not applied any kind of activation. Without activation, it can produce any value like -infinity to infinity. So that is why we have to write from logits is equal to true. From logits is equal to true means binary cross entropy will also expect values from -infinity to infinity. Like if you apply some kind of, let's say, sigmoid activation, then in the last layer of like here in the last layer of the discriminator, then what will happen is that the output will be between 0 and 1. The discriminator will give such values. Then you can put from logits is equal to false, so that the loss is tuned to expect values in that way. So this, you have to do these things in order to train a better model. That's just some kind of things you have to take care of while you are designing your own model. So now we come to the discriminator loss. So what is the loss of the discriminator? As sir had told, like in case you have a real output, the discriminator should classify it as 1. In case you have a fake output, the discriminator should classify it as 0. So now you put these kind of loss functions. Let's say for a real, you are having a real output. the discriminator should classify it as 1. If it is doing anything else, then that is a loss for the discriminator, right? So and if there is a fake output from the if we are providing a fake output, then the discriminator should classify it as a 0 instead of a 1. So if it is doing anything else, then that is loss. So these two terms, if you add, then that will give you the loss for the discriminator. Now if we move to the loss for the generator is trying to fool the discriminator, right? So for every generated output or the fake output, it should the discriminator should give a 1. For whatever image the generator is generating, it is a fake output, and the discriminator should say that it is 1 instead of a 0. So that is kind of the thing that the generator wants to achieve, right? So if the generator is not able to do that, then that is a loss for the generator, right? If anybody has any confusion with the loss functions, then you can raise your hand and ask. Okay, so basically these are the loss functions, and there is something called the optimizer, which is able to it is able to define what kind of updates will be done to the weights and biases once we start training the model. 1e-4 is basically the learning rate. So this learning rate is used to update the variables, which is you can change these values. These are also hyperparameters. You can change and see what kind of updates are done. So we have to define two different optimizers, one for the generator, one for the discriminator. And then these are checkpoints. These are some things to keep in mind. If you are training the model, you want to store the weight somewhere so that you can use it later. And yeah, so with these kind of definitions, you can just start training your model. So you start from some noise vectors and then pass it to the generator. The generator will produce one MNIST image, and then you compute the loss function based on what you defined, and that way you start training. So for each training, for each step of the training, this is what is done. So you start with a noise vector, and then this is something called tf.gradient tape. Gradient tape is basically used to record what kind of things is happening inside the model, so that after this all these functions are done, you can call the tape.gradient. Tape.gradient will compute the gradient of every kind of operation that was done inside the model, and then it will pass those gradients to the optimizer. The optimizer will then change the weights of the generator and discriminator accordingly, right? So this is one training step, and this at tf dot function, this kind of a decorator is necessary for TensorFlow to create an optimized graph of this entire thing. I don't think you have to be very thorough about this right now, but just keep in mind that you have to use that decorator, otherwise your training will be very slow, right? So now this is the training part. You are just calling for you are starting training here. You can define epochs to be anything. Let's say you are training for 50 epochs. You can, epochs means basically how many times you want to run the model, like how many times you want to generate outputs and compute loss and update the model. So let's say you want to train it for 50 epochs. You can write epochs is equal to 50, and you run through the data set, compute the losses, and then update the model weights. And this line is just to record the loss functions over training, so you can see whether your training is converging or not. So your loss will start stabilizing after several epochs. Now these are some helper functions just to print the outputs of your model after some epochs, and these are just to save your files. Now I'm not going to go through the details of that, but you can see that after training for around 50 epochs, this is the kind of output the model is giving. Earlier it was giving this noisy output, right, the generator. Now after training for 50 epochs using all this code and every kind of training, you can change the hyperparameters and see, but this is the kind of output it is giving. So even though it is not perfect, but you can keep training for more epochs and just see it will start improving more. So this is, let's say 9, this is kind of 9, this is 7. in your hackathon you have to generate let's say alphabets, English alphabets instead of these digits. So these are some extra things, like you want to restore the latest checkpoint that your model has stored in this directory. So you can just go through these lines later while implementing. And this is one interesting thing that you might observe while training. So in case of a generative model, your loss function may not be very stable, like it will not start reducing after, like continuously reduce after some epochs or something like that, which you might expect from other models like classifiers. So what happens is basically the generator is trying to produce very realistic images, whereas the discriminator is trying to differentiate between the real and generated images that it is getting. So once the like you can look at the generator loss, once the generator starts producing some kind of real images, that means the like when the generator starts producing very realistic images, the generator loss starts getting lower. But what happens at the same time, the discriminator is not able to distinguish between the real and fake outputs. That's why the discriminator loss will increase when the generator loss is getting lower. So this kind of a two-player game keeps happening between the generator and discriminator during the entire training process, and after some time they start converging. So yeah, so this is something to observe. If you want your model to train well, you have to observe these kind of loss curves and just predict if your training is stable or not. If your training is not stable, let's say the discriminator loss will be always high or the generator loss will be always low, or something different will be happening. So that is just a way to check if the model is working well or not. Yeah, so these are some extra helper functions. I think that's it about the implementation part. It's just like a walkthrough to let you to get you started with everything. So yeah, you can post any questions related to this tutorial or further if you have. Yeah.
So how do we decide that the model has converged based on the loss curves?
Yeah, you can decide that based on the loss curves, or let's say you see that the output is becoming very good after some epochs, you can do that. Like, it's up to you. Yeah.
So we have to take care of two losses, right? So is there some band that we should look for, that discriminator loss should be around this much, or in such a range of the generator loss or something?
Yeah, you like the losses should not be highly showing a lot of variance at the end. Like if they have converged, then they have to come to some kind of a value, fixed value, or they should not be having a lot of variance.
Even then, that part I get. For
Yeah.
single loss, that is what we look at. For two different losses, we get to that. But what if the discriminator loss is very high and the generator loss is very low towards the end, when they are sort of
Yeah, so that is some kind of like the model is not trained well, I would say, in that case. So
they should always be nearby.
yeah, they should be nearby.
Please don't leave, guys. Right now we have a couple of announcements also after this. Doubts, if anyone has, you can ask right now. So it's necessary that everyone of you join the teams for the hackathon. So please make sure you have joined the team. Can we show that slide?
Yeah.
QR code once more?
So,
Yeah, we'll share the slides and we collaborate.
On Teams,
Yeah, we'll share the slides and we collaborate on Teams itself. So it's very important that every one of you enroll yourself on Teams so that you can participate in the hackathon.